In power engineering, stability analysis begins with an idealized baseline, a single synchronous generator connected to a grid of infinite mass and constant frequency. This curve defines the steady-state power-angle relationship. As the internal rotor angle increases, electrical power output rises until it reaches its maximum limit at exactly 90 degrees. The equal area criterion balances area 1, accelerating energy absorbed during a fault, with area 2, the decelerating energy expelled. For stability, these must match. Post-fault, the operating point drops to the lower curve, significantly reducing power transfer capacity. If the kinetic energy gained during the fault exceeds the available recovery area, the rotor angle pushes past its stable limit. The generator slips a pole and loses synchronism with the network. While the equal area criterion is a learning tool, this single machine model misses the interactions that occur during a decentralized grid collapse. Real power grids possess finite inertia and consist of an interconnected web of synchronous machines, varying from utility-scale turbines to smaller industrial units. Under normal conditions, these machines are separated by low transmission impedance, allowing them to operate as a single composite unit. They remain locked in step by sharing synchronizing power across transmission lines, keeping their physical rotors rotating at the same electrical frequency. A major disturbance disrupts this synchronized operation. A fault alters the network impedance, forcing individual generators to manage their own mechanical torque without the support of the wider grid. Surviving a transient event requires distributing the sudden surge of kinetic energy across the entire network before any single machine spins out of control. When a severe three-phase fault occurs on a transmission line, the disturbance propagates through the network corridors. The drop in electrical power causes mechanical torque to rapidly accelerate the rotors of the generators closest to the fault location. Engineers define a critical clearing time, the maximum duration a fault can persist before instability occurs. Machines physically closest to the strike absorb the most energy, risking exceeding this limit. This chart shows 4 machines responding to one fault. Machine 1, closest to the strike, absorbs too much energy. Its rotor angle lockets upward, losing synchronism. Meanwhile, machines 2, 3, and 4 are further away. This greater electrical distance keeps their excursions bounded. These surviving machines experience synchronous oscillations, or swinging. They wobble in frequency before the oscillations damp out, and the units return to a steady state. A machine's stability during a grid transient depends on its electrical distance from the fault and its individual rotational inertia. Industrial cogeneration plants and independent power producers now supply a significant portion of grid capacity. These cogeneration units typically have much smaller inertia than utility-scale generators, meaning they accelerate much faster during a disturbance. To limit fault currents, many cogeneration plants use series reactors at their connection points. While these reactors protect equipment, they also create a loose electrical coupling between generators located within the same facility. This loose coupling can trigger a phenomenon called hunting. Following a grid disturbance, adjacent units begin to oscillate against each other, drifting out of phase. During hunting, the 2 units trade real and reactive power back and forth in a localized cycle. This is a low-frequency oscillation localized to the plant, distinct from the violent transient instability that leads to widespread pole slipping. Adding independent power sources introduces localized dynamic risks that traditional infinite bus models do not account for. When a utility grid fails, an industrial plant may perform islanding to protect itself. The tie line opens, severing the physical connection to the grid. Once isolated, the plant's survival depends on the balance of power flow at the moment of separation. In one scenario, the plant may have been generating excess capacity and exporting power to the utility. The sudden loss of the utility load creates a massive power surplus. The isolated generators rapidly accelerate, pushing the local frequency into a dangerous overfrequency zone. If the plant was importing power from the utility to sustain its processes, the separation creates a different crisis. The plant now has a mechanical power deficit. The electrical load is greater than the available generation, causing the local system frequency to drop. To stop the frequency decline, the plant uses automated load shedding. Non-critical operations are disconnected to bring electrical load back into balance with the mechanical torque. Islanding transforms a grid-wide voltage problem into a localized race to balance torque and load. Engineers design the infrastructure to withstand these multi-machine transients through physical interventions. Reducing transmission impedance keeps generators electrically closer together. Lowering impedance increases the synchronizing power transfer margin, allowing the system to better handle disturbances between different grid areas. Fast-acting protection relays and circuit breakers are also critical, as they minimize the time a fault stays on the system. Physically reinforcing the grid and shortening fault durations reduces the kinetic energy rotors must absorb, preventing them from slipping poles. Beyond physical design, grids use active electronic defenses called power system stabilizers to manage oscillations. A power system stabilizer modulates the generator's internal voltage by adjusting its field excitation in response to rotor speed changes. This modulation injects damping torque into the machine, creating an electrical force that counteracts the physical swinging of the rotor and stabilizes the frequency. These controls are highly specialized. Damping localized hunting inside a cogen plant requires a different algorithmic profile than damping inter-area swings that cross an entire continent. Transient stability in a modern grid is a coordinated interaction of networked inertia, high-speed switching, and active algorithmic damping.